Hello, guys. Welcome back to the MJ School of Mining and Geology YouTube channel. In today's lesson, we are dealing with the exploration of groundwater. So basically today, we're going to be looking at different maps. We're going to look at the location map, the geological map, hydrogeological map, the topographic map, and see how these maps, they help us in what you call the exploration of groundwater. But don't forget to like, share, comment, and subscribe to our YouTube content. But above all, don't forget to hit the notification button below so that you get notified once we upload new content. So the first thing that we're gonna deal with, checking what you call the location map. For example, if we were to look at this area, this is the area in Limpopo province in South Africa, especially the Maha. So basically, I'm just giving you the example. Right. So here we're looking at this area, and then we've enlarged this map, and then we zoomed in, and then here we are checking in. If we check here, this is our location map. So a location refers to a specific geographic point or area on the Earth's surface where the hydrogeological conditions are studied. Okay, we are talking about the presence and the behavior of groundwater. So by knowing the location would help determine where groundwater resources are found. All right, how deep they are and whether they are aquifers, whether are in aquifers that are accessible for the extraction. So that's why we need to understand or know them, the location. All right, where we wanna or do what you call our hydrogeological studies. Okay, so the location affects the groundwater quality due to the surrounding geological formations, potential contaminant sources, and natural factors like mineral content or salinity. For example, if we are doing our hydrological studies near the mining areas, or near the farms where we have got a lot and lot of agricultural practices, and we know that during over application of fertilizers and pesticides, they might get to be wiped by the rainfall and then go into the rivers, and then we know that surface water are interconnected with what you call the groundwater, and then so it means if the surface water is contaminated, also the groundwater will be contaminated. So we need to know the location. We need to understand more about the location. Where are we basically doing our hydrogeological studies? So the geographic location would help identify areas where groundwater is naturally replenished, recharge zones. Okay. And the discharge zones. Okay. So the accurate location data is very important for suitable water management, ensuring safe drilling sites, protecting against contamination, and planning for efficient use and conservation of groundwater resources. So this is our location area, and if we check here, we also have got highly dense rivers. All right, we've got more rivers, and we know the more we have rivers, the more we're gonna have the groundwater recharge, and the more groundwater recharge, the more the groundwater occurrence. So automatically we know that this side is gonna be disaster because we don't have much of the rivers. But here we have got high rivers, and then the high rivers, because of we know the fact that the groundwater, the surface water and the groundwater are interconnected through the permeable formations, and they recharge one another. So basically that is the location map, and is very important in hydrological studies because it shows the location of the area, and then it will be telling us that wherever the location we picked, we are far away from the contaminants or whatnot. All right, and that environment is very safe for drilling. The other map, which is very important, is what you call the geological map. Sorry. So a geological map is very important. Okay, it's a critical tool in hydrological studies. Why? Because it provides a detailed information about the geological features of an area. So it will tell us more about geological features, and these geological features would affect the groundwater occurrence, the movement, and the quality. That is to say, the contamination and the movement, the permeability, and the groundwater occurrence. All right. So for example. We are checking basically we are okay. So what am I doing? Sorry about that. Okay, so basically we're gonna be checking our rocks. Okay, we're gonna checking our rocks. So if we can check on our map, we can see that the Leboa granite occupies a larger area, and then it follows by the Rustenburg Lesuit. Okay, it follows by the Rustenburg Lesuit, and then yeah, basically we've got lot of Lebo granite, and then less, and then followed by the Rustenburg suite, and then we've got Pretoria group shales. So remember, the shales, they act as the aquicludes. They act as aquicludes. Okay, sorry, they act as aquicludes. Okay, so we've got the shales as well, and then we've got else do we have? We've got this Eka shale, so they're also Monyana a bit. Yeah, basically that is that. So these geological features, they're gonna affect the groundwater occurrence. So for example, let's look at what we call the what you call the groundwater occurrence. So if we were to look at this, for example, the Leboa granite, these are what you call the fractured aquifers. Okay, so these are the fractured aquifers. Okay, so most of our rocks over here, they are fractured aquifers. So these kind of aquifers, they are typically found in consolidated rocks. Okay, so for example, the granite as mentioned, okay, or the Leboa granite, and you can also find these in rocks such as basalt and many other crystalline rocks, basically. Okay, so the groundwater now would be stored and then transmitted through the fractures and the joints and also faults. Okay, but now these things, they need the parameters that were mentioned in one of our videos. Go and check it. The parameters that are needed during the borehole siting. We have to check at the connectivity. We have to check at the of these fractures. We have to check the density. The densities, never mind my spelling, that you have to check the density, we have to check the persistence, we have to check and many other things, and all these parameters, they must complement. So in fractured aquifers, we the groundwater can and can move, provided we've got the parameters which are complementing each other. That is to say, the fractures, they are cross-cutting each other. They are we've got the connectivity, we've got the density, and many other aspects. And we're also checking what you call the apertures and stuff. All right. So that is what you call the groundwater occurrence. For example, if we have the rocks such as limestones and dolomites, because we know we're gonna have a high amount of what you call the dissolution channels. Okay, we're gonna have a high amount of dissolution channels, creating more cavities. So we know we're gonna have high groundwater movement and high groundwater storage in such rocks. So that's why we're saying these things. These maps, they will tell you much about the groundwater occurrence. So we're gonna know what kind of aquifers are we dealing with. All right. Are we dealing with the intergranular aquifers? Intergranular aquifers are those that are of unconsolidated sediments. We're talking sand, gravels, and many other things like sandstone. Okay, so we are checking that. We are checking what kind of aquifers are we looking at? Are we looking at an intergranular aquifer? Are we looking at a fractured aquifer? Are we looking at what? Are we looking at karst aquifers? Okay, but also we don't have to neglect the aquicludes, shales, for example. So we know that aquiclude, it's a geological formation which does not transmit the significant quantities of water due to the very low permeability. All right. So clay particles, okay, they do not transmit a lot amount of water because of the low permeability. Okay, that is what you call an aquiclude. For example, shale. Okay, shale can be a common example because shale, it consists of fine-grained sediments that would inhibit the groundwater flow. All right. So for the shales example or these aquicludes in terms of the groundwater occurrence, okay, these shales, they would act as barriers. Okay, they would act as barriers for the groundwater occurrence. Okay, so they act as barriers for what you call the groundwater flow. So they do not store or they do not transmit. They do not store, or rather, they do not transmit what you call the water efficiently. So it means now the groundwater may accumulate above the let's say this is the aquiclude. So the groundwater may accumulate above the aquiclude. All right. Now, if the groundwater accumulate above this aquiclude, we can have what you call the perched. Okay, we can have what you call the perched water table. We can have what you call the perched water table. Okay, so now we have to understand that when we have got the areas with aquicludes, okay, these areas that are typically not suitable for the groundwater extraction, or therefore they are not good for the borehole siting. Okay, but it's not that these shales they are bad stuff. No, they've got the good side of it. Okay, that is to say, these shales they can also serve as what you call the confining layers. They're not that bad. Okay, yes, they are not good for borehole siting, but generally, but they can also um, what we serve as what you call the confining layers. So confining layers, that is to say, let's say the top part and the bottom part, they channel the water. It means, and this they are good to avoid contamination because now we know if the surface water and then is contaminated and is trying to recharge these, then they're gonna be blocked somewhere here, and then they're not gonna be recharged, provided they are consistent. But in such cases wherein they can pinch out, let's say here they pinch out, yay, then they recharge, then they are no longer confined. And then if this water is contaminated, it's gonna contaminate this water. All right? Yes. So that's why we're saying they can still serve as confining layers, okay? And this would prevent the downward the migration of water, all right? And then making sure now that the water quality within this aquifer is excellent, all right? So they're very important. Okay. So you'd agree with me that uh, okay, you'd agree with me that no matter how bad you are, you can always be used as a bad example, all right? So these aquifers, these aquicludes, sorry, they beside not being good for siting the borehole sites, but they protect and make sure that the groundwater that we drink is of high quality. Okay, because they can confine our aquifers. So, which is why the geological map is also important. So, the hydrological map is a specialized type of map that provides information about the distribution, the movement, and the quality of groundwater, okay, within a specific area or area of interest. So it integrates the geological, or it incorporates the geological, hydrological data, hydrological and hydrogeological data to represent the subsurface features such as aquifers. Okay, we're gonna see the type of aquifers, and then we can also see the groundwater flow directions. We can see the recharge and discharge areas and the groundwater quality. Okay, and these maps are often used. These maps often use various symbols, colors, contours to depict different hydrological conditions and characteristics. So these are just you know for a reference and for example, or for the purpose of this presentation. All right, this map can include so many other things to see the recharge and many other things, but now here we just included the type of aquifers because I'm just generalizing things. Okay, but this map you can also it can also um what you call show what you call they have what you call contour lines, and then it can also determine the flow directions, and many other aspects they can also be included. So here today, for the purpose of this presentation, I'm gonna interpret only the type of aquifers. For example, here we've got the fractured aquifer, we've got the aquiclude, we've got the karst aquifer, and many other things. All right, you remember this region was the Boer granite, the topmost unit of the famous Bushveld complex. Okay, so and yes, so we have to understand what type of aquifer are we looking at. So for example, here this region at the southern part, okay, um we see that we've got the karst aquifers. Okay, so I've mentioned that the karst aquifers they will develop in soluble rocks. We're talking limestones, we're talking dolomites. Okay, because now these rocks are susceptible to chemical reaction. That is to say, we're going to be talking about what you call the dissolution processes. Okay, these dissolution processes would create the cavities, or would create caves, or would create sinkholes. Okay, so and what you call the under underground channels. Okay, so we're talking limestones, we're talking dolomites. Okay, so because these rocks, for example, limestone is a calcium carbonate, but if we've got hydrothermal fluid that is coming in with its magnesium and substitute it somewhere here, then we're gonna have magnesium rich calcium carbonate, which is the dolomite. All of these things, they've got calcium carbonate. So this calcium carbonate, during hydrothermal fluids, especially the slightly oxidized hydrothermal fluid, it can dissolve this calcium carbonate and then cause forming what is called a dissolution channels. And then we've got dissolution channels. We're gonna have caves, sinkholes, under groundwater channels. Okay. So now, in terms of groundwater occurrence, the cave sinkholes and whatnot, or the karst aquifers, basically, they are very important. They are very, 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 very important because these things, they are characterized by their higher permeability. And not only that, it's not only limited to high permeability, but also the rapid groundwater movement. Okay, because of we've got these high conduits, or the passages, okay, or the channels through which groundwater can flow. And because now we've got these underground channels, these things, these channels, they can also start. That is to say, they can store large amount of water. Okay. Where we have got, for example, the Transvaal supergroup, the Transvaal supergroup, the Transvaal supergroup have got especially the lower portion. Okay, it has got these dolomites, and then we've got the likelihood of forming these the karst aquifers, and then the more groundwater occurrence. So here, got the people who are sitting here when they can drill, they can find more groundwater. All right. So can now see that the karst regions, they are potential sites for high yielding wells. Okay, or for example springs as well. Okay, but you must consider something that if you look at the fast flow because of this high permeability, okay, we're gonna have the unpredictable pathways. Okay, so these unpredictable pathways they can be prone to what you call contamination. Okay. So the only problem with this, it will be the effect of contamination because they are prone or they're susceptible to contamination, and the kind of contamination is unpredictable. Okay. So, but the aquiclude, I've already mentioned that the aquiclude is good and sometimes can be bad, you know. So we talked about that, especially where these people, they're gonna suffer. These people, they're gonna suffer. So you can now see that hydrological map, especially when showing you aquifers. Okay, you can understand here a lot more things. So let's check at this Rustenburg-led suit also of the Bushveld complex. So it's also at the what you call the fractured aquifer. So it's also a fractured aquifer. So I've already mentioned that we can find this thing in basalt or mafic rocks, or any crystalline rocks, basically. All right. So you need to, these rocks, they need to undergo tectonic deformation, that is to say, faulting and folding, okay, creating some fractures. And then those fractures, they need to be they need to be connected, they need to be persistent, and many other things, so that we can have high groundwater occurrence and the permeability. And then if we can have okay, we've got the last part, the intergranular. Here we're talking the sandstone. Look at this part. The people who are sitting here at the edge, they're gonna have high ground occurrence. Okay, because the intergranular aquifers, we're talking about the aquifers that consist of the unconsolidated sediments. Okay, we're talking sand, we're talking gravels, we're talking sand particles. Basically, we're talking sand particles, we're talking gravels. Okay. And then we know that if we've got sand particles, even if you go you have your sand, okay, you can pour water on that sand, and then you're gonna see we're gonna have a high amount of infiltration. So because the sand have got more pore spaces, okay, between the grains, okay, and then so the intergranular aquifers, they would have the pore spaces between the grains that would store and transmit the groundwater. Okay, so in terms of the groundwater grains, the the regions which are they're underlain by high intergranular aquifers, they're going to experience high groundwater occurrence. So if you were to if you were to map these areas, okay, you're going to see the groundwater that will be primarily stored in the spaces between grains. Okay, that's why we say intergranular, between the grains. All right. So which these areas would typically be good for the groundwater extraction. Okay, why? Because there is a high porosity and the permeability. Okay, so during borehole siting, these kind of areas, they would be prime targets. Okay, so overall, okay, overall, if we are, let me remove these things. Okay. 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 Good. All right. So in general, in general, so if we want the groundwater potential, would need the regions. If we were to compare the two maps, if we were to look at the aquifers, so in general, we have to basically look for the intergranular and the karst aquifers, because these things do generally have high groundwater potential. Okay, but we don't say the fractured aquifers, they don't offer the potential. Okay, they still offer the potential, but we need more fractures, and those fractures, they need to be well connected. Okay, they need to cross cut each other. Okay, so I hope you understand. So we are targeting the intergranular and also the karst aquifers. But if we can consider the parameters, the connectivity, the density, the aperture, and many other parameters when we are mapping the fractures, and then the fractured aquifers, they can also serve as the good um, regions for a borehole siting. Okay, so the last map would be the topographic map. So this map, they show the highland and low land areas. Okay, they show steep and flat areas. And so the topography, they play a significant role in controlling groundwater occurrence. Okay, it controls the groundwater occurrence, because if, for example, we were to check over, let me, okay, okay. So here, for example, we've got high topographic relief. Here we've got high topographic relief. So here it's like we've got this steep slope, and then here is like we have got almost flat surface. Okay, so that is the difference between the two. So in this region, for example, these regions, they are almost flat. And then these regions, they are almost steep. So you'd agree with me that if we've got like this, provided if we've got the flat surface, provided we've got more vegetation in hydrogeological studies, we need the vegetation, because we know the more vegetation we have, the more we're gonna have the infiltration, but provided the slope is flat, and then we do not have the runoff. If we don't have a runoff, we're gonna have more infiltration. And then remember, provided we've got vegetation, we're gonna have infiltration, and then we're gonna have a high groundwater occurrence here. So and if here we're gonna have a high groundwater occurrence, and provided we also have got high rivers, we are checking different aspects. If we've got more rivers, then we know we're gonna have high rechargeability. Okay. And of course, that rechargeability, it also depends on the fractures. If we've got the fractures which are well connected, we're going to have high groundwater occurrence. That's why here, generally, we have got a high groundwater occurrence that here. So because now, if we've got um, high slopes, we're going to have, for example, this. If we were to pour water here, will flow. Okay, we're gonna have the runoff, and then we know the runoff it does not promote what you call the infiltration. So we're gonna have less infiltration. So if we've got less infiltration, we're gonna have less the groundwater occurrence. So good people, this brings us to the end of the exploration of the groundwater. So basically, we were looking at different maps that we can use during the exploration of the groundwater. And also we have a video wherein we are looking at the parameters that we can map, especially mapping the fractures for the borehole siting. Okay, so we've got many other things that we can consider during hydrogeological studies. Okay, we can also consider what you call geophysics, using the the seismic method, the electromagnetic method to also confirm what you call the groundwater occurrence. All right, so basically today we're looking at just maps which can help us to explore the groundwater. All right, I hope you enjoyed this session. If you did not understand, you are more than welcome to drop the question in the comment section and we will be pleased to assist. All right. But above all, thanks for everything. Please support us by sharing the channel, subscribing, commenting, and also hitting the notification button so that once we upload new content, you are the first one to get the notification. I always like to say, until next time, cheers.